Hi everyone, welcome to today's Berkeley seminar. Today we are pleased and honored to have Priyaa Srinivasan, who will be talking to us about communicating relational thinking. So Priyaa has been working on a book, as some of you know, on a book on applied category theory called Relational Thinking, and I'm sure today it will be a very interesting discussion about that and the broader set of ideas. Priyaa, whenever you're ready.
Thank you, Shavi. First of all, I would like to thank everyone for being here, for giving me your time to listen to this talk. And I want to thank Sophie for arranging this seminar, making it fun. And Shavi helped me to calm down and prepare this talk. So thanks to Shavi too. Okay, so a precursor, I am moving soon, so I had very little time to prepare this talk. I'm going to pretend for the next 1 hour the rest of the world doesn't exist, even though I'm on camera, and just talk to you all, and I hope this will be a good conversation between us. And whatever project I'm presenting today, this is joint work with Angeline, Paul, and Brendan. We would see their pictures at the end. So thank you. Not really. So I would like to take this moment to thank everyone at Topos. This has been a great year for me. I mean, I don't want to cry now, but these are the work days that I will be physically present in Topos. So, thank you, everyone. I can't express enough, with words, how much I'm grateful to be here and to work with David, to work with Brendan. And anything more, I'm gonna cry, so I'll stop here. This video, so my experience of learning category theory is not unique. Each one of us face hardships, struggles to go through the math, in its form. So here is how I would like to think about the learning experience. So we have CT at the core, category theory, and then recently applied category theory is growing. And then Brandon used to, one of my friends, Brandon, he used to use this word applied category theory when they take applied category theory and then apply it to their field. So as we are inviting more people into category theory, and we want to share the goodness of the math with the world, I feel like it's valuable and important to recognize that we need more methods of communication to get the math or categorical ideas to people out there. So CT is traditionally, we use symbols, we use mathematical symbols, formal language to do math, to document it. Symbols are quite powerful because they eliminate ambiguity. They eliminate the room for interpretation, and they give us a trustworthy platform in which we can communicate ideas, and they are also easy and very precise to document. They are very concise. But then now we have technology, so and symbols use minimal technology. We write on the board, we get black pens, and then we print papers. So the technology that goes into using this form of communicating math is quite economic. But now we have technology, and we have the power of technology to find, to venture into new modes of communication, and which can complete the symbol. So our hope is that we can utilize technology to complement symbols so that we can give a wholesome presentation of categorical ideas. And I got all these thoughts after completing a recent project. This is not where I started, but this is where I ended. The project, so the project we recently completed is a free online textbook. It's on category theory. So it's a textbook on categorical thinking and implementation. And this is the cover of the book. Even though it's online, we designed a cover. So today's talk, I just want to walk you through the story of the book, the contents, and also the technology behind this book. So I think those are my two main goals for this talk. Okay, so if anyone wants to see the book, we have the URL of the book is tinyurl.com/ourthinking, and so all the source code, everything is online. It's open source, and if you go to the GitHub, we will publish these slides. but all the code repository for the book as well as the code in the book is available here. So, content. Any questions so far? Any discussions? I jumped right into the content. Okay. It's in categorical quantum mechanics. Thank you. Right. So this project was funded by Mozilla. I'll give more details at the end. But we started this project somewhere in November, and Brendan and I were starting a discussion how to do it, what to do. Like the specification we had for the project was like quite simple. Like it's extremely simple. It's like develop an inclusive online open source material on algebraic Julia. It's like, and we had all the flexibility to experiment with this idea, whatever we want to do. And so we wanted to develop a motto. What do we really want? So we wanted this material to inspire and empower people. So our goal is not just to teach, but for readers to feel inspired to go and explore, and they feel empowered at the end of this material if they get through it. And now, open source is fine. Like it's going to be open source by default, so I'm going to ignore that part. So if you want to communicate algebraic Julia to lay audience, like so it's like communicating algebraic Julia is a twofold problem, right? So I hope everyone here is aware of algebraic Julia. Should I? Okay. Oh, okay. So algebraic Julia is a online. So it's a programming library in Julia for implementing category theory. So we can code using category theory there. So whenever we learn a programming language, so when I first learned C, I didn't have to learn what numbers mean. I didn't have to learn what data, like it's like I didn't have to know what are alphabets. Like it's all there, like, and we are just taking that concept we already know in the real world and bringing it into the programming computational world. So there was no need for me to learn the concept, but there was need for me to learn the structures, the structures that were provided by the programming language, like if loop, while loop, and those were the things I learned. But if we venture into algebraic Julia, the problem is twofold. Now we are talking about structures in the real world that we are not familiar with. So like algebraic Julia allows us to implement like category theory, like in our solutions. So we first have to know what does it mean to think categorically, even to use algebraic Julia, right? So that's the first thing. So the structures are like, usually the readers are not familiar with the structures, and then we have to teach them how to use algebraic Julia. And so this is a twofold problem, and combine this problem with the word inclusive. It's like, if this project was not impossible, it was like quite challenging and interesting, and we didn't even know how to, like, it was quite hard to get started, like how to, where should we even start, how to make all this inclusive, and then we had 3 months to finish the project. I was like, wow, okay. But we had a great team, and Evan was helping us all along. That was like awesome. So this is the mantra we followed throughout the project. Simplicity is the key. We don't have to worry about telling people less. Like keep things simple as possible. So for the first part, the categorical thinking, we decided we would not use any technical jargon. So to make the material inclusive. So use approachable layman language. So that's something we strictly followed throughout the book. So we stayed away from any formal definition, but at the same time, we didn't want to sacrifice on the math as well. So that's like choosing the terms, at the same time, getting the readers back to the literature was like, we tried to hit a balance there. So the first term we sacrificed for this approach is category theory itself. So Brendan came up with this term. So it's like category theory, we are going to scare away people. It's not going to resonate with most of them. So let's use the word relational thinking, because that's what category theory is about. So we started with systems thinking, and we get into relational thinking. And we don't tend to explain this term, but we try to give an experience of what relational thinking is throughout the book. And the second thing is like, so what media are we going to use to communicate relational thinking is that we chose directed graphs. So something as simple as possible. Like we can't get simpler than this. So we chose directed graph and made the central theme or the storyline of the book is double push out rewriting on directed graphs. So that's all this book is about. But like it's not all, okay, so this is the central theme of the book, and if we take a category theory book, this will be done in 3 pages, right? But this book took 9 chapters, like to explain this concept slowly. Right, so the plot of the book is this. So so this is what Paul came up with. This is like simply amazing. So like the whole, like the 75% of the book is explaining this ladder of abstractions, taking the reader through each rung in the ladder, and then finally when we reach here, it's like hiking, and then we get to the top and see the view. So that's the idea. And also like as we move, so we start with directed graphs, a very visual form. Like this is how I have been introduced in my high school to directed graphs. So, but as we move up the ladder, directed graphs transform from being a visual tool to a computational tool. So that's, and also like as we go up the ladder, our focus shifts organically from a single graph to relationships between graphs. Like we don't have to say it. As we climb up the abstraction, we see like we are gradually shifting our attention to relationships, and when we reach here, we see that relationships is what counts more than the individual pieces. So this is in my view, it's a very beautiful story to see that transformation happening and get some insights out of it. And this is where all the computation happens. And this is purely human language. Yeah, any questions here? Okay, so maybe for the next 10 minutes, I will just like walk through the book, like the different contents of it, like the different chapters of it. So we start with chapter 0. So the reason for 0 is like we started with 1, but then we realized like we need another chapter. We were like, okay, let's put a 0 there. So chapter 0 for directed graphs. We start with a very simple situations, like introducing graphs where like this is a situation where a person can like start at the lodge, take a lift up to the mountain top, and then if they know downhill skiing, they can go to an isolated village and then cross-country ski there. At that point, they're stuck there. They have to find some other mode of transport to come back, but then they can take a chairlift down back to the lodge. So this situation is explained using graphs. So the idea is that we can model real-life situations using graphs. And as I said, like the central theme of the book is double push-out rewriting. And so this chapter sets up the problem. So it says like, okay, like in real world, the situation changes, right? So when the situations change, we want to update our graphs. But graphs are really fragile things. Like when we update, what if like we have some edges like by themselves, like the dangling edges, like when we do computation. So it's like telling us something like very ungrammatical sentence. It's not like having a right meaning or wrong meaning. Like stop the language from being ungrammatical, like the sentences from being ungrammatical. How do we do this? So how do we set up this so that we know our method is foolproof? So that's the problem we start exploring in chapter 0. And then after introducing chapter 0, we have a slight interlude on dynamical systems. I should thank Sophie for really inspiring me for getting into algebraic Julia. She showed me the algebraic dynamics package. So in this chapter, we have like 2 friends talking to each other. One is grumpy, the other one is happy, and then how they are going to affect each other's mood levels. And like, so this is a dynamical system, and we start from the scratch, and then like we come up with some equations or some dynamics to explain each one's mood and how each one feed into each other. And like code all this and even find the graph how like their moods change over time. So this is the grumpy friend whose mood level is like below -2, and then here is a happy friend, And then like as they interact, you see like they both like, so the happy friend is becoming grumpy, but the grumpy friend is becoming happier, and they meet, and then like the system gets to an equilibrium. And all this is completely done, and the data is generated by algebraic dynamics package. And so this, we don't expect the readers to understand coding here. It's just like the setup and how to think about these problems. But after chapter 2, we come back. Oh, okay, I shifted the order. Okay, so chapter 1 is on data. So now we are going up from rung 2 to rung 1 to rung 2 in the ladder of abstraction. So here we start with the visual thing. And this is the definition I learned like when I started category theory. A graph is a pair of functions from the set of edges to the set of vertices, right? So this is where like we introduce how to think of graphs like in a way where a computer can understand it. Like this, humans can read visually, but how do we represent this data so that a computer can work with the graphs, right? So that's where like we introduce this definition where we take each edge and map it to the source of each edge. Like so source of this is diamond, like that. And then with the target, we have the same idea for the target of each edges, right? Any questions here? Yes, David? Oh, okay. So the question is, why do we choose this? Why can't we flip? So here, like we are saying, like the definition of a graph is a pair of functions from the set of edges to the set of vertices, right? Why can't I think in the opposite direction? What goes wrong if I say that if I want to capture this data like this, like it's all captured, like this is the same graph, right? But why would it not work in the general case? So this is like asking the reader to think about it, like what goes wrong if you switch, like you ask if we ask the vertices to be the domain and the edges to be the codomain. And so for every question we ask in this book, we answer right there. We don't leave any question unanswered. So we say like, so in the arrows first approach, every edge will have a source, every edge will have will have a target. That means that no edge is by itself without unconnected to a vertex, right? So we get a good graph even if we take like a set of edges and set of vertices, just place random arrows in between them, that will be a graph. It's guaranteed to be a graph. But if we go the other direction, we ask the set of vertices to be the domain and the set of edges to be the codomain, and we just like connect them randomly, what comes out won't be a graph always. So that's the idea. So that in that sense, we are justified that we are choosing the pair of functions to go from the edges to the vertices. So that's it's like the idea we wanted to communicate is like, why is finding right abstraction important? Like, right. So that's chapter 1, and then 2 is interlude. Chapter 3 and 4, we go further up. So these are blueprints. So here we talk about schemas. So that's, we are slowly entering into the categorical world. We are saying like how we can bunch up, like, so even this data here where, so this is maybe a source or a target map, like where the function from the set of vertices to the set of edges can itself be like thought of as a graph by bunching up all this information into one arrow, like representing all that by one arrow. So a directed graph schema at that point would be like this bulky arrows from arrows to vertices. And then once we put the data in, so this is like, I would like to think of this as a blank form which says like name, write your name here, write your first name, write your last name here, write your age here. So this is just giving that specification of what goes in here, what goes in here, what goes in here, and what goes in here. And once we fill in this data, we get a certain graph. So this is like at that point, schema is like a blank form, and then like we can just distribute these forms to different people to see different manifestations of graphs. So that's kind of the idea that's communicated. And yeah. And then once we understand the concept of schema for directed graphs, we can talk about schemas at for multiple things, right? Like now we can go to reflexive graphs. So schema is like, at this point we talk about commuting diagrams. A schema is like, for a reflexive graph is this blank form and the data should satisfy this information. So if we start, so what is this saying is that if I take an arrow, look at its source, and then if I reflect it, I should remain in the same source. So it's a reflexive graph has a self loop at every vertex, right? So that's kind of the idea. And similarly for undirected graphs, we have that schema there. So every Petri net has this schema, and then simplicial set schema. So we can just generalize the idea like slowly to multiple levels. So that's kind of the idea here. So this is all covered in chapters 3 and 4. And chapter 5, we arrive at the our final ladder, which is for final rung, which is categories. So here we realize, like, once we have a schema, we can think of a universe where the universe has all possible instances that these schemas can generate, right? So this is like an example of that universe. So if we start with an undirected graph schema, then we just like think of the universe with clouds where each cloud has a graph instance in it. We don't have to generate, but we know such a thing can exist now that because we have the schema. But if there is a universe where no one's aware of no one else, what's the point of that universe, right? So at that point, we are forced to think about the relationships between these different instances. So that's when we go to graph morphisms schema, and then we generate this whole universe of graphs where each graph, there are relationships between graphs. So that's our foundation where we can talk about double push-out rewriting. So that's when, this is in chapter 5, and yeah. Any questions so far? Maybe I'm going too fast. Yes, Evan?
How did you make these animations?
Paul made it. So you hire an illustrator and ask him to make it. But I don't remember the software which he said he made it, but I'll ask him.
Cool.
Yeah. Right. So now that we have the foundation to think about graph push-out, now we have the foundation to think about the universe of graphs, where this universe has only graphs and all possible instances of the graphs and relationships between them. We can talk about graph push-outs. So now, our first urge was to tell them how to compute a push-out. But it's like, no, that defeats the purpose of the book. So how would you explain universal property to people without talking about categories, functors, and natural transformations? I welcome you to think about it for a moment. Like, we haven't introduced anything else. We just have that universe. How would you talk about universal property there? Yes, Sophie?
I feel like I would do it intuitively, really. It's always like some best.
Yeah.
This one.
Yeah.
And that's
You got that.
universal property.
Yeah, you got that. That's like you got it. It's the most natural thing that you could ask for. But getting to that most natural thing was how do we do it? So when we wrote this chapter, we realized all we have to do, so we can't really talk about push-out as an individual. Like, a push-out is like inherently related to the graphs of which it is a push-out. So we can't talk about push-out as an individual object. So it is about relationships, right? So the easiest way, or like the most natural way to explain this, is to ask repeatedly to all the relevant graphs, what is your relationship with the push-out? So let's, if we go here and think about this, you start here and say, if I want to compute the push, so push-out is like obtained by gluing this graph and that graph along their overlap, right? So you ask, how would I expect myself to be related to the push-out if I am the overlap? How would I expect myself to be related to the push out if I'm graph A or graph B. So that's when we get our first commuting diagram, right? So we want to know like wherever these two graphs overlap, if I start from the overlap, I should end up at the same position in the push out. So that's the kind of the idea, and that when we ask that question, we get like a certain number. So the push out can be any graph in the universe, but there are only a few graphs which will satisfy this condition. So at that point, we have narrowed down a little candidates, right? Okay, so then what we do? We ask the same question to the candidates who had been filtered. So that's when whatever Sophie said comes, like she says like, for any other graph which satisfies this requirement, if you are a push out, you will have exactly one arrow there. And we explain this in the book very slowly, like I see squinting and thinking, but we explain this slowly, but it's very easy to see at that point, like for any other graph, like sometimes we have like a back arrow, sometimes we have multiple ways to map like a non-push out to a push out, or no way to do it. But when it comes to a push out, there is exactly one arrow into every other candidate that has been filtered. Now, so that's good. Then we filtered our candidates further, and then we ask, okay, now we have a few more candidates. Who do we choose? Who is the push out? Again, we ask the same question, and then we realize all the people, like all the graphs which satisfy these conditions are isomorphic. So that's how we explain the universal property in chapter 6. Yeah, so at the end we realize like the universal property is another name for harmony of relationships. So any object that satisfies that property is interacting harmoniously with every other object that's there. So that's something that came out. And chapter 7, we take the idea of push-outs and then explain double push-outs. So, okay, this is the diagram for double push-out, but I'm not going to explain what double push-outs are. But there is something to wonder, right? Like, how did so here is, let's explain this. So we have a host graph where we want to do some modification, and then we know what the pattern we want to find inside this graph and the pattern we want to replace it with, but there is an overlap between them. So whatever we find, how to replace is given by this overlap. So that's the idea. So this is all the data that's given. The gray things are the data that's given. So once we start this process of computing the, like making the modification using double push out, the math, the first thing it does is to remove the edges that, like in the modification, we are going to remove some edges and vertices and add some vertices and edges, right? That's how I think of the modification. So what the math does is to first remove the edges that needs to be removed, edges and vertices that needs to be removed. So it first does the removal, and then whatever new things needs to be added, it adds to the graph. So now this is amazing. How did the math know that it should first remove and then add? Like we can do the other order, but it's messy, right? Like you first remove the things you need to remove and then add. How did math know that order of processes? That was simply amazing. Like it just worked out by itself. So yeah, I thought like it's a thing of beauty. So that's, we first compute the complement and then the push out. So then I realized, okay, relational thinking is actually a good form of thinking because we can rely that it would lead us to good places. So that's, we were convinced about that. And then in the final chapter, we discussed some serious applications like opening a cake box without dropping it, how to do double push out here, right? And some explanation around that, and there is code that has implemented this, and also like making a cheese sandwich. So here we have moved away from graphs because we are in the world of which is generated by any schema. We can apply the same idea beyond graphs to explain these ideas. Right, so that's basically the content of the book. I'll just keep going because I really want to get to this part. so that's the first thing, like how to communicate categorical thinking without using formal language. So that we got through the first part. And then the second one is like, how do we explain algebraic Julia without wanting them to program? Like that was too full. But Evan really did rescue us here by showing the technology that we could use. Let me see if it's ready. I really hope it's ready. Oh, damn, okay. Okay, so maybe I could just explain it here. So this is the book, and whenever we wanted to show code for algebraic Julia, we could just like, binder is down, I think. So we say live coding, and then like this code part is like we have already provided the code, and then the user just have to run it, and they can see the output. The server is not ready now, so I'm not running it. But like if I press run now, it's going to say waiting for the kernel. And also like this code is editable. I can write stuff and then see the execution. So all the setup is already done in the server for the user. They don't have to do anything in their computer. So that's something that really made this book possible. Right. So I want to talk a little bit about the technology behind the book. So the infrastructure of the book, this online textbook is given by Jupyter book. So this is an environment to build, like they say, publication quality documents from computational content. It supports like LaTeX and all markdown features. And this is compiled locally and viewed in the web browser. So let's see the book quickly. So here is, is it visible? Okay, so this is how the book looks when we go to the URL. So we have all the content here, and there are like subsections that's shown on the other side. And then we have these like Jupyter book provides these environments where we can like put notes or like have some collapsible boxes and stuff like that. And also like at the end, we can go to the next chapter and then like all the information. So this is the basic layout of how a Jupyter book looks. And how to compile this book, it's very simple. The setup is quite simple. If we go to Jupyter book website, they have this tutorial, create your first book, get started with references. Look, so all I did is to follow this, and it's very simple. Like I didn't have any trouble following their instructions. And once we have that, the book gets going, and we go to, and to build the book locally, all we have to say is Jupyter book. Sorry, the font is too small. Jupyter book build in whatever directory you want to build, and it builds, and it generates a URL here, and we have to just copy paste and put it in our browser. I didn't start any server or anything, and it's there, like the book is there locally. So that's something that was quite neat. And yes.
That one would run the puzzle?
It won't run the puzzle. We need more technology to make it run stuff. Good question. That's my next slide. And then, okay, play. Okay, and then all the configuration file is in config.yaml. If you like to work with this technology, I would recommend have a look at the repository of the book, because all the configuration is there. And as David asked, how would we run the puzzles like the algebraic Julia code? It is run by connecting this Jupyter book to a server, and the server is provided by Binder, MyBinder. So this is an open source computing environment for Python, R, and Julia. Like Brennan and I were saying, this is too good to believe that it's true. It's like, how can they give like their computing resource free of cost? There was no security or anything. We didn't even have to create an account. It's like, how can that even be possible? But it's possible. So they provide a sandbox of 2 gigabytes of RAM, and we can, once we say what kernel we want, they have like a Docker file which will install everything. And what we found is that it's ideal for small scale projects. So Evan and I spent hours and hours like trying to figure out it for Julia. It was a little bit hard to get Julia going, but it's worth it. And okay, and we don't blame the binder. A lot of it is because like Julia's resource-heavy language, we were asking a lot from them. Like, so the setup was a bit hard. And I didn't even have to refer to binder website for setting up anything. And so once the server is there, the live code execution is enabled by something called TB. So I can show you the link here. So TB is, so this is the TB documentation. They make it clear, like we can, for any static HTML web page, how to add live code there is explained clearly in this documentation. Should I just say play? And it's very simple to configure TB in Jupyter book. So it's like, this is the configuration. I just have to say TB true and binder hub URL, and then it's there. And then our greatest trouble was finding the right name to invoke the binder. Like we were trying Julia 1.10, we were trying all sorts of things before. It was like random. We had to, yeah, all sorts of combinations. But once we got it going, it's quite easy. And there is a lot of documentation available for Python and R. Julia was a bit hard, but then I must say, like, the community is really welcoming and good. So any questions we asked, we got answers right away. So having a good community, open source community around these sort of projects is extremely important, I feel. And then there are other fun tools we used, like Sophie introduced us to Javis, which is a Julia package. It's like we took the results, like the numbers generated, and we could do some visualizations. So this is all in chapter 2, which is like the interlude chapter. And also like Canva is a graphic design tool. Topos has free access as a nonprofit. We have free access to this tool. And this is quite great for anyone to use. And one of my friends designed the cover for the book using Canva. So a lot of like, and you can also make posters, presentations in this tool. So I highly recommend it for everyone. And okay, so I'm almost here. So here is the people. I didn't like to use the word authors because like there is much more going on than for a physical textbook in a material like this. Like it's a great group work, and there is like writing is a major part, but there is much more going on. So I tried to say like concept and content. So concept and content was by these people here, Angeline, Paul. Paul did all these amazing animations and illustrations. And Paul also he's very enthusiastic about category theory, but it comes from the non-category theory background. So his knowledge and vision was very helpful in shaping the project. I was thinking more like a mathematician, but he pushed us towards like a one coherent storyline. So Paul did a great job there, and he also did the illustrations. Brendan and Angeline there. Brendan and then myself. Technology, we could not have done it without Evan. So he was there throughout, helping us. He is the one who introduced us to TB, and he helped us getting going with algebraic Julia, setting up things. He was always there whenever I needed his help. So we set up the technology together. And then there are scores of people who made this project happen. So Sophie, she is the one who got, like the first month of the project was fun because of Sophie. Like she showed me, like walked through the algebraic dynamics package and everything. Pavel inspired that Kiki Booba example. And yeah, David helped me write the schedule. And he's like, whew, okay, this is doable, this is doable. So David helped me get started, Beth, Owen, everyone. And these are my friends who designed the logo on the cover. And Chris coded all the examples in chapter 6. So, and Owen helped us with the technology as well. So thanks everyone. And this project was funded by a grant from Mozilla. It's by Mozilla Internet Ecosystem Program. So their mission is to advance the internet and to ensure it remains a force of good. So, so this is a collaborative project between Topos and Mozilla. And I would like to end my talk with this, something that my friend wrote, but it deeply resonated with me. I'm going to just let the audience read it instead of me reading it. And this is the message I want to leave with for you all. Thank you. Let's take a moment to read this. Thank you. Okay, questions?
Can you explain the picture on the front cover?
Oh,
It looks
yes.
a little bit like the Topos logo, it seems, or maybe I'm wrong.
Sorry, Shavya. Which one? Okay, this in the beginning?
The front cover of the book.
Yeah. This one, right?
Yeah. It looks a little bit like the shape of the Topos logo, but I could be wrong.
It's infinity as well, a little bit like infinity. We wanted Topos colors. Okay, but first it's pretty. That's one of the main reasons we chose it. But it was actually a spherical. It was more geography thing. So we was like, no, we have to make it math. So we changed the shape to infinity. And then like it also came out like Topos logo, which was like quite nice. So that's
So
why.
it's really one.
It's one loop, yeah. There is not many, no. It's all joins and goes, so it's one loop. Yes, Sophie.
I have a question about the choice to like not use formal language.
Yeah.
First of all, like I'm sort of curious, like in the chapter about categories, like what do you say? And then my second part of that question is like I always feel conflicted about this because I know jargon can be off-putting, but at the same time, if you don't learn the jargon, you can't participate in like the discourse. That feels like a really complicated question to me.
You exactly captured our voice when we started our project. So I think it depends on who you are writing for. Like we were torn between, even like in this ladder of abstractions. Where is it? Sorry. Oh, okay. So in this ladder of abstractions, we were torn between using categories versus universe. Or like here for data, we wanted to use world, blueprints, and schemas. We were like, how are we going to like really bring the audience to the math world if we are not introducing the jargon, right? But again, it depends on the audience to whom you want to talk to and what's the goal. Like our goal was to make them think about these concepts and then provide references if they want to go further deep in, but also mention in the book, by the way, in mathematical literature, this word is called that, but we will stick to this in this book. So it's like touching it slightly, but choose, like there is no good way, like you have to give up something. So that's what we gave up. We gave up the comfort of having that jargon and bringing people into the formal language, so that we had to give up. It depends. It's such a matter of choice, I think, subjective. Does that answer your question?
Yeah. Can I see in the text or?
Yeah, of course. Yes, let's do it.
Questions would be great.
Let's do it.
If we have time, I'm curious, like what the chapter on categories.
Okay, so this is the chapter on categories. So this starts by saying like, okay, so once we have all these schemas, there are infinite number of graphs that we can generate, but we can't do that. It's not practical. So we're just going to think of a universe where we have all the instances, but the universe is boring if every object existed by itself without any connection, right? So then we start talking about connections. What does it mean for one graph to be related to the other? And that's when we talk about morphisms and like what is a morphism? Like how can we, like this is not we can't have a dangling edge, right? Like we can't. So how do we really do this mapping in the right way? What is relationship between graphs? So that's something we talk about. And then from there you can go into like the commuting diagrams, this part, like what is a graph morphism? This is not a morphism, so, and how it should be. And then finally we get to the schema. Once we have the schema, at the end we have, where is it? Yeah, it's coming. Yeah, so here, like each one of this blue box is a graph, and then together with the morphism we have like a relationship between these two graphs. And once we have relationships, we can talk about that picture, right? So that at that point we talk about category. But to get to that, yeah, it takes a lot, step by step.
What do you expect to be the use of the book? I mean, do you expect it to be taught in educational contexts? If so, which, like philosophy or writing or?
That's a great question.
And the related question is, in the process of writing it, did you test the text with people who could stand for the audience?
That's a great question. Thank you. So the second question is easier. I'll answer that first. So because of the timeline we had for the book, which was just like 3 months, 3 to 4 months. Yeah, November to March. So we didn't have lots of time to go get the book to the outside world, like ask the readers to read it, provide us feedback. But we ran with our intuition and our team was diverse. It was not just mathematician. We had a person who had worked in like a exploratorium, who has built exhibits to explain math concepts. So for his non-math background was very valuable. It was an asset for the project. So we had like these different thought processes that's coming into the project. If it was written only by mathematicians, maybe it would have been a different sort of book. But having this diverse team really helped. And I also have written like 3 blog posts, and me presenting this talk is an invitation for people to read the book and give us feedback. So that's the.
Can you continue to revise the book?
Yes, because it's online, that's better. So then we can. Yes. So at the beginning of, actually, thanks for asking that question. At the beginning of every chapter, like we do say, like there is a Google Doc where you can put in your comments, and so we wish there is a better commenting feature in Jupyter books. We don't have that yet, but we refer the readers to the category theory Zulip and stuff. So that's.
Did you get another grant for revising? Is that the right book?
You should ask Brendan.
Well, also you said the code's on, like, there's a GitHub repo that has all of it there.
Yeah.
Another way you can do it is with just like GitHub issues. Like actually.
Oh yeah, maybe raise GitHub issues. Okay, so that's and regarding the use of the book. So first thing, what I realized like at the end of this project is that this book is a creative nonfiction in mathematics. It's like this is one of the first. I don't know. I mean, at least I do not know any other material like this. So this is an experiment, and we have got this far. So like the main purpose of the book, the meta purpose would be to encourage more materials like this to think differently. Like even that question, how would you explain universal property without categories, functors, and natural transformations? But it seemed impossible. But trying to do it just opened up such orthogonal views about the concept. So it's an invitation for mathematicians to think about in a little different orthogonal language and utilize the technology. It takes a lot of work, but I think it's quite worth to bring more people in. And regarding the textbook side, I think this material would need more work to become a education material in a school or something. In that setting, it's not there yet, but it's a good material for an adult learner, like who is interested in even if they know category theory, just reading this and seeing like if it resonates for them in a different way, like about category theory. So for category theory audience, non-category theory audience, to get a feel of this material I think that's what is the purpose of the book, and to connect to the community. I think that's one of the broader purpose of the book. But it would be really interesting to see how different people interact with this material and to collect some information on it. Does that answer your question?
Yeah. It's responsive to the question. Maybe way I mean, I would pick out building the community as something that
Yeah.
this seems to be the kind of function this is supposed to have, and the way you organize this production is symbolic of that.
Thank you. I agree. Maybe invitation for more grants for material like this. Yeah. Sophie?
The one thing would be for users, they might not know that they don't do relational thinking, or they might not know that they do relational thinking.
That's right.
And somehow, you know, and they probably both are true. Probably they're doing it and they're not doing it. So as you present that general idea to people, it would be good to locate this thought.
That's a great point.
So probably people do it, but they don't do it as either as well or as collectively as they might. This will help them.
Right.
This might help people. You know, there's a lot of literature on making yourself smart. Okay. And this sounds like it could fit that, right? And smart in that you can connect up things that you have come across and experienced in many different, I don't call them domains, but you can't make sort of use of all these bits. Say something about some other domain because you don't have the ability to get from one thing to the other.
Yeah.
So, since a lot of people want to look smart, you know, and they have to prepare for interviews with McKinsey or whatever, I mean, this would be a great way to help them.
As long as we can get people to do relational thinking, I think we achieved our purpose there.
Well, I think
Or be aware of
do
it.
People, your whole point is people do it.
All the
They're
time.
simple diagrams.
Yeah.
The question is, can you do it? Can you make it a thing for yourself so you can do it better, so you can do other things better? I'm sure you can make a graph out of that.
Thank you.
That would be a nice graph.
Nice graph.
Great. Thanks, Angeline. Thank you so much, Priyaa.
Thanks, Sophie.